In this video, we will learn Einstein's postulates in detail. So one consequence of the Galilean transformation is that two observers, one at rest and the other is moving with constant speed relative to the first, could not agree that the value of the speed of light in vacuum is c equals 3 times 10 to the 8 meters per second. Now the question is, what determines the particular reference frame such that if an observer is at rest relative to this frame, this privileged observer will measure the value of the speed of light in vacuum, c. So it was believed that the privileged observer was the same observer for whom Maxwell's equations were valid. The space in which the privileged observer is at rest is called the absolute space. And since light is an electromagnetic wave, it was thought of by scientists that a medium must exist through which light propagated, and they call this medium the ether. An experiment that was developed by Michelson in 1881 and refined by Michelson and Morley in 1887, we call this the Michelson-Morley experiment, is an effort to detect the ether. However, the result of this experiment sadly shows that no ether was detected. Now, the one element common to both the null result of the Michelson-Morley experiment and the fact that Maxwell's equation hold only for the privileged observer is the Galilean transformation. But these obvious transformations were re-examined by Einstein from what might be termed an operational point of view. Einstein took the approach that any quantity relevant to physical theories should, at least in principle, have a well-defined procedure by which it is measured. And if such a procedure cannot be formulated, then the quantity should not be employed in physics. And Einstein could find no way to justify operationally the Galilean transformation of time. T prime is equal to t. That is the statement that two observers can measure the time of an event to be the same. Consequently, the transformation t prime equals t, and with it, the rest of the Galilean transformation was rejected by Einstein. So here are Einstein's guiding idea, which he called the Principle of Relativity. So, postulate number one, the laws of physics are the same or invariant in all inertial or non-accelerating observers. And the second postulate states that the speed of light in vacuum is the same in all inertial frames of reference and is independent of the motion of the source. So let us elaborate the first postulate. Suppose there are two identical vans, both are moving at uniform speed on a straight, smooth road. Consider that a passenger 1, is riding in one of the vans at a constant velocity of 25 meters per second due west. Now let a second identical van, being driven by passenger number 2, approach van 1 from behind at a uniform speed of 30 meters per second relative to the ground. When this van comes into view, passenger 1 makes some measurements and conclude that he is traveling relative to the passenger in the van at 5 meters per second due west. On the other hand, if passenger number 2 measured your speed, he would also conclude that passenger 1 is backing up toward him with a relative speed of 5 meters per second. In other words, both passengers each determine that the other is moving with a relative speed of 5 meters per second. But one cannot make physical measurements that would determine whether you are moving, he is moving, or both of you are moving. Furthermore, the results of an experiment performed on any physical system on one van must yield identical numerical results to those obtained by the passenger on the second van, when he conducts the same experiment on an identical system in his van. So, passenger 1 in van 1 measures the frequency of the horn from his van to be 550 Hz, and the speed of light from the signal light of his van to be 3 times 10 to the 8 meters per second. And likewise, passenger 2 in van number 2 measures the frequency of the horn from his van to be 550 Hz, and the speed of light from the signal light of his van to be 3 times 10 to the 8 meters per second also. Now, what about the situation where passenger 1 measures the frequency of sound produced by the horn in van 2, and passenger 2 measures the frequency of sound from van 1? So, they will have dissimilar measurements, that is, according to the classical Doppler effect. Now, what about the situation where passenger 1 measures the speed of light from van 2's headlights, and passenger 2 measures the speed of light from van 1's taillights? They will both obtain c plus 5 meters per second. But this is inconsistent with Einstein's second postulate. According to Einstein, both passengers would measure the relative speed to be c, which is equal to 3 times 10 to the 8 meters per second, since the speed of light is invariant and independent of the relative motion between the source and the observer. Surely, one must find this hard to believe and most remarkable. However, every experimental examination of this phenomenon verifies the truth of Einstein's second postulate. Serious experimental verification of Einstein's second postulate was not possible until the technological advances of the 20th century. Perhaps because of this, the invariance of light was not realized nor even seriously contemplated until Einstein published his work on relativity. It was his remarkable insight and understanding that brought about an intellectual and philosophical revolution and made man recognize the limitations of his dimensional experience. So we will now deduce the basic results of Einstein's special theory of relativity. So these are the consequences of Einstein's postulate. We have the relativity of simultaneity. Simultaneity is not an absolute concept anymore. Events that are simultaneous in one frame are not necessarily simultaneous in a second frame, moving relative to the first. Another is time dilation. If two objects or if two events occur at the same space point in a particular frame of reference, the time interval between the events, as measured in that frame, is called a proper time interval. If this frame moves with constant velocity relative to a second frame, the time interval between the events, as observed in the second frame, is longer than the proper time interval. And we also have the length contraction. So if two points are at rest in a particular frame of reference, the distance between the points, as measured in that frame, is called a proper length. If this frame moves with constant velocity relative to a second frame, and the distances are measured parallel to the motion, the distance between the points, as measured in the second frame, is shorter than the proper length. The details for these consequences of Einstein's postulates was discussed in the previous videos that I have shared to you. So let us answer some sample problems. So here are useful equations. So for time dilation, we have this equation. Delta t equals gamma times delta t prime, where delta t prime is the proper time. And then we have the equation for length contraction. We have delta L equals delta L prime over gamma, where delta L is the proper length. Gamma here is equal to 1 divided by the square root of 1 minus u squared over c squared. We can also let beta be equal to u over c. So for the first problem, we have to find the values of gamma for the given u. So we just need to use the equation for gamma. We have gamma is equal to 1 over the square root of 1 minus u squared over c squared. And then we substitute the value for the first u. We have 1 minus, we have 0.84 raised to the 1/2 c squared divided by c squared. So we can cancel this out, and we're left with 1 over the square root of 1 minus, we have 0.84 raised to the power of 1/2 square, that is 0.84. So this is equal to 1 over the square root of 0.16, or 1 divided by 0.4. So this is equal to 5/2. Okay, so this is for u equal to 0.84 raised to the power of 1/2 c. Next, solving for u equal to 0.6 c. We just need to use the equation for gamma. We have 1 minus 0.6 c over c square. This is equal to 1 over the square root of 1 minus, we can cancel this out, so we are left with 0.6 squared, that is 0.36. So we have 1 divided by the square root of 0.64. This is 1 over 0.8, which is equal to 5 over 4. And then for u equals 0.8 c, we just have to redo our calculation. This time the value for u is 0.8 c, so we have minus 0.8 squared, since your c in the numerator and c in the denominator will cancel out. So we have 1 over the square root of 1 minus 0.8 squared is 0.64. This is equal to 1 over the square root of 0.36, which is equal to 1 over 0.6. And we have 5/3. And then lastly, calculating for gamma with u equals 0.866 c, we have gamma is equal to 1 over the square root of 1 minus 0.866 squared. This is equal to square root of 1 minus 0.75. We have 1 over the square root of 0.25. So we have 1 over 0.5, or this is. Notice that all the values of gamma are greater than 1. So for the second problem, we have to express gamma as a series using the binomial expansion. So gamma, which is equal to 1 over the square root of 1 minus beta squared, where beta equals u over c, can be written as we have 1 minus beta squared raised to the power of negative 1/2. So for a binomial of this form, we have 1 minus x raised to the power of minus n. This can be expanded into this form, 1 plus nx plus n times n plus 1 divided by 2 factorial x squared plus n times n plus 1 multiplied by n plus 2 over 3 factorial x cubed plus dot 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 to infinity. Okay, so in here we have 1 minus beta squared raised to the power of minus 1/2, where our n here is 1/2, and then our x is beta squared. So we have 1 plus our n, which is 1/2, times our x, which is beta squared, plus 1/2 multiplied by 1/2 plus 1 over 2 factorial, that is 2 times 1 x squared, that is beta squared squared, plus 1/2 times 1/2 plus 1 times 1/2 plus 2 divided by 3 factorial, that is 3 times 2 times 1. We have beta squared cubed plus dot dot dot. Okay, so we have 1 plus 1/2 of beta squared, plus we have to evaluate this one. This is 3/2 times 1/2 divided by 2, so that is 3/8 beta to the 4th. So 3/8 beta to the 4th, plus we have this one, evaluate this one, we have 3/2 times 1/2 multiplied by 5/2 divided by 6. So that is equal to 5 over 16 beta to the 6. Okay, so this is the binomial expansion for gamma. So for the next problem, we have two inertial systems that are receding from one another at a uniform speed of 0.6 c, and in one system, a sprinter runs 200 meters in 20 seconds, according to his stopwatch. If the path of the sprinter is perpendicular to the axis of relative motion between the two systems, how far did the sprinter run and how long did it take him according to observers in the other inertial system? Okay, so suppose the two systems are moving. So this one, we have here an inertial frame of reference. This is the x-axis. This one is the z-axis. And another inertial frame of reference, we have x prime. This one is z prime. So this one is moving at a speed equal to 0.6 c. So in one of the systems, so the sprinter runs 200 meters in 20 seconds. The path of the sprinter is perpendicular to the axis of relative motion. So for example, at z, the sprinter runs 200 meters. Now, since the motion is along the x, or the motion of the systems is along the x, then delta z prime, the observer will also measure the same value for delta z prime. So the other observer in the other inertial system will also measure the distance of the sprinter to be equal to 200 meters. Now, take note that for speed near the speed of light, delta t is not equal to delta t prime. In fact, we have this equation, delta t is equal to gamma times delta t prime. Okay, so if in one system a sprinter runs 200 meters in 20 seconds, then at the other system we can measure the time, or the observer can measure the time to be equal to gamma times delta t prime. So gamma times 20 seconds. Now gamma is equal to, we have already solved for the value of gamma for 0.6 c in the previous problem, and that is equal to, so 5 over 4. Substituting it into the time dilation equation, we have 5 over 4 times 20 seconds. So we have 100 divided by 4, that is equal to 25 seconds. Okay, so this is your delta t as measured by the observer in the other inertial system. Now, what if the sprinter's motion is along the axis of relative motion between the two systems? If the path of the sprinter is parallel to the axis of relative motion between the two systems, then there will be differences in the measurements of the distance and the displacement of the sprinter. So we have delta x is equal to delta x prime over gamma, where delta x prime is the proper length. So substituting, we have delta x prime is 200 meters, while gamma is equal to 5 over 4. So we have 4/5 of 200 meters, that is equal to 160 meters. Okay, so this is now your delta x as measured by the observers in the other inertial frame of reference. And your delta t is just equal to the previous delta t that we have obtained, which is 25 seconds. So for problem number 3, take note that the path of the sprinter is perpendicular to the axis of relative motion. That is why there is no difference in the measurement of the distance that the sprinter has traveled. And for this problem, the path of the sprinter is parallel to the axis of relative motion. That is why uh, the different observers in the different inertial frame of references obtained different results. For problem number 5, an observer moves at 0.8 c parallel to the edge of a cube having a proper volume of 15 centimeter cube. What does the observer measure for the volume of the cube? Okay, so we can draw a cube with sides equal to 15 cm, and we suppose that the observer moves parallel to the x-axis. So this one The motion of the observer is along the x-axis where u equals 0.8 c. Now to solve for the volume, we need to know delta x, delta y, and delta z. But you have to take note that the observer is only moving along the x-axis. Therefore, your delta y, delta z is just equal to delta y prime and delta z prime respectively. And we only have length contraction along the x. So we have this equation. So this is equal to 15 cm. This is also equal to 15 centimeters. While this one, delta x equals 15 cm divided by gamma. For 0.8 c, we have measured the value in problem number 1, and that is equal to 5/3. So we have 3/5 of 15 centimeters, that is 9 cm. Therefore, the volume of the cube as observed or as measured by the observer is equal to, so the volume of the cube is equal to delta x, delta y, delta z, delta x times delta y times delta z. This is equal to 9 cm multiplied by 15 centimeters times 15 centimeters. So this is equal to 2025 centimeter cube. So for problem number 6, two inertial systems are uniformly separating at a speed of exactly square root of 0.84 c. In one system, a jogger runs a mile in 6 minutes along the axis of relative motion. How far in meters does he run, and how long does it take the observers in the other system? Okay, so for this problem, we're given with u, which is equal to the square root of 0.84 c. So this corresponds to gamma, which is equal to 5/2, as solved in the first problem, problem number 1. Now we are also given with the length interval, which is equal to 1,609 meters. So say for example, this is along the x-axis. So we have delta x prime, or the proper length, is equal to 1,609 miles in 6 minutes. So this is your delta t prime, the proper time. Okay, so for the other observers, we can get delta x by using the length contraction equation. So we have delta x prime is equal to gamma. So we have 1,609 meters over gamma, which is 5/2. So we have 2/5 of 1,609 meters. So this is equivalent to 643.6 meters. So this is according to the measurements made by the observers in the other system. While your delta t is equal to gamma multiplied by the proper time. So we have 5/2 multiplied by your delta t prime is 6 minutes. So we have 30 divided by 2, that is equal to 15 minutes. Okay, now for number 7, consider two inertial systems separating at a uniform speed of 3c/5. If a rod is parallel to the axis of relative motion and measures 1.5 meter in its system, what is its length to observers in the other system? So again, we're given with u, which is equal to 3 over 5c. To find gamma, we have to evaluate. We have 1 over the square root of 1 minus 3 over 5c divided by c squared. Cancel c out. So we have 1 over the square root of 1 minus 9 over 25. This is equal to 1 over the square root of 16 over 25. So this is 1 over 4 over 5, or this is equal to 5/4. So this is the value of gamma. Now if a rod is parallel to the axis of relative motion and its proper length is equal to 1.5 meter, then delta L is equal to 1.5 meter over 5 over 4. So we have 4/5 of 1.5 meter. So this is equivalent to 1.2 meter. So let's proceed to problem number 8. The proper mean lifetime of pi mesons with a speed of 0.9 c is 2.6 times 10 to the minus 8 seconds. Compute their average lifetime as measured in a laboratory and the average distance they would travel before decaying. Okay, so for this problem, we are given with the proper mean lifetime of pi mesons. So this is the proper time, delta t prime, which is equal to 2.6 times 10 to the minus 8 second. And we are also given with u, which is equal to 0.9 c. Okay, so first, we need to find gamma. So gamma is equal to 1 divided by the square root of 1 minus 0.9 squared. So we have gamma is equal to 2.294. Okay, now we can now solve for the average lifetime of the pi mesons as observed by a laboratory observer. This is equal to delta t, which is equal to gamma times delta t prime. So we have gamma, 2.294 multiplied by 2.6 times 10 to the minus 8 second. So we obtain 5.965 times 10 to the minus 8 second. Now, in order to calculate the distance that they would travel before decaying, we need to recall this equation for the speed. So, speed is just equal to distance over time. Therefore, distance is equal to the speed times time. So, what is the value of speed? So, this is equal to 0.9 c meters per second multiplied by the time. So we have 5.965 times 10 to the minus 8 second. So we have 0.9 times 3 times 10 to the 8 meters per second multiplied by 5.965 times 10 to the minus 8 seconds. So we obtain 16 meters. Alright, so for your assignment, you have to submit the solution to these two problems in the Google Classroom. Okay, thank you so much for watching this video.